The coefficient of correlation and the coefficient of determination are two important concepts in this chapter. If the coefficient of correlation between x and y is close to +1 or -1, indicates that we can use x to predict y. However, the coefficient of determination goes further. The coefficient of determination measures the contribution of x in predicting y. If we disregard x to predict y, we can observe that the minimum value of y is this, and the maximum value of y is this, and y take value between these 2 points. Then the best estimator for y is a value in the middle of this range. The mean of all value of y is the best estimator if we don't take in consideration x. Let's compare the deviation of all value of y with respect to the mean of all y when we disregard x with the deviation of all y predicted by my mathematical model. We can obtain the deviation of all value of y respect to the mean of y, square all of the deviation, and sum all of the deviation square to obtain the sum of the square of all deviation of y respect to the mean of y. If we use y bar to predict the value of y, could be good for all members of the population located here, but is not good for those, neither for those. Let's calculate the percentage of error that we can make using y bar to predict the value of all y when we use our mathematical model. In this way, we can obtain the coefficient of determination, which measures the contribution of x in predicting y. We use the equation of the line to explain the relationship between x and y. For any value of x, suppose that we select this value of x. Then in my sample, the corresponding value for this x sub I is this value, y sub y. With my model, this is my model, the corresponding value for xy according to my model is this value, explained by my model. My model states that the mean of all possible value, if we select all possible value in the population that have this measurement and we measure y for all of them, all of this value will be around this number, which is y hat, is the value that we can predict using my model. If we have no information, if there is no relationship between x and y, the minimum value of y could be this value and the maximum value of y could be this value, and we can obtain the mean for all of this value, and the mean could be located approximately here, the mean of all y. We can obtain the deviation of all y's in my data respect to this line. If we use the mean of all y as a horizontal line, we can obtain the deviation. That is the total deviation. Total deviation of y is the deviation of each observation respect to the mean of all of them. The square of all of these deviation is the sum of a square of all y. But this sum of square is measured respect to the mean of all y. It's very important. The deviation of all y, all observation, respect to the model, the deviation of all yi minus this value, which is different to this, as you can see in this. When we square all of this, that is the sum of square of all error, because it's this distance minus this distance. Actually, is this distance. This is the error. When we sum all of this sum of all square represents the sum of square of all error. And if we subtract from this distance, the distance from this value to the mean, this distance, from this distance we subtract the error, we have this distance here. This distance represents the contribution of my model to reduce the total error when we use y bar to predict y sub I, which is the real value. Then when we compare this the difference between this distance minus this error, we obtain this quantity. And when we divide this distance, the sum of a square of all y's minus the sum of square of all error, and divided by this quantity, the sum of a square of all y, we have this quantity, which is the variation in y that is explained by my model, divided by the total. For that reason, the coefficient of determination is the percentage, this ratio is the percentage of the deviation in y explained by my model, actually this distance, divided by the total deviation respect to the mean of all y. That is the interpretation of the coefficient of determination, the proportion of the variation in y explained by my model when we compute the deviation respect to the mean of all y. That is exactly what we are going to do in the next exercise. That is the formula for coefficient of correlation. This formula is explain sample variability in y respect to the mean of all y divided by the total sample variability of all y respect to the mean of all y. That is the proportion of total sample variability explained by the linear relationship. And that is the interpretation. Coefficient of determination is this ratio and represent the proportion of the total sample variability around the mean of all y that is explained by the linear relationship between x and y. Let's do one exercise. Then in this exercise, I recommend to do this using technology. You can do this problem using StatCrunch, and if you want to show your work, I recommend to use Excel. And in Excel, you can obtain all of these values. The sum of all xx, the sum of square of all y, the sum of square of all xy, and all of these values. Remember, we can do that in Excel. The only thing that we have to do is substitute all of these values in this formula. The sum of the square of all y is this number, 6.97, is here, 6.97, minus the sum of the square of all error. Remember, the sum of the square of all error is the value in my sample minus the prediction of my model. That is the error of my model. But we obtain all of the deviation, we square and we sum all of this square to obtain. But the shortcut formula is this one. Remember, we did one problem using this formula before. The sum of all square error is the sum of all y minus b sub 1, the slope, times the sum of square of all xy. When we substitute all of this value that we obtain in Excel here in this formula, we can obtain the sum of the square of all error. And when we substitute the sum of the square of all error here, the sum of the square of all y, this number here and here, divided by the sum of the square of all y, we can obtain the coefficient of determination. Another way to obtain coefficient of determination, besides technology that is given in second, we can square the coefficient of correlation. When we square this quantity, we will obtain, when we square this quantity, we will obtain the coefficient of determination. Two different ways to obtain the coefficient of determination. But the most important thing is the interpretation. Because if the coefficient of determination is 97%, that coefficient implies that my model in which I use the number of employees in this city, or number of employees in casino, explain 97% of all variability in the crime rate in the city. The variability in the crime rate is a good predictor. It's a good predictor for the crime rate, the number of employees. But that is not the reason of the, remember, there is no causality. It's used as index, like economists use several index to predict situation in economy. The index is not the cause. It's used to predict. There is a correlation between these two variables. The interpretation is, our interpretation is as follows. We know that using the number of casino employees to predict the crime rate with the least square line, this square line, account for nearly 97.4% of the total sum of the square of the deviation of all y value above the mean. Or state in other way, 97% of the sample variation in the rate crime can be explained by using the number of casino employees in the mathematical model. That is the interpretation. Is very important that you understand that. Let's stop here.